This one's going to be about topic 6.3, which is applications of differential calculus. So we're going to be discussing second derivative, concavity, and what that has to do with local maximum, local minimum, which is like in reference to stationary points, as well as points of inflection. So in order to continue with this lesson, which focuses on second derivative, we want to kind of remind ourselves of what we know. So far we've learned about the first derivative, and we know this as the gradient of the tangent line on a graph, or the rate of change of a function, and it's usually seen in this function notation right here. So the change of y over the change in x. And so we've previously found this out through the power rule, the chain rule, the product rule, or the quotient rule. Any of those help find the derivative. And then we graphically see that usually depicted like how it is here. So you have the function represented by this gray line, and it looks like a parabola. And so then we have these like highlighted tangents, and so usually we find the gradient of those tangents, and that's how we find the derivative. But each of those different tangent lines have different derivatives, so that's something to think about as we go into like this new information we're going to find out about. So what we're finding out today is about the second derivative, and so that's sort of like the main emphasis of 6.3 and what the second derivative can help us find out about like graphical behavior. And so the second derivative refers to the rate of change of the rate of change. And so it's usually seen with this function notation right here, and it comes from the fact that if we have like this whole function right here, that gray line, and we zoom into like just this section, all of these rates of change, all of these derivatives are positive, but depending on where you draw that tangent line, oh, go away. I'm not recording it because she did it like 4 times before that. Okay, so depending on where you draw that tangent line, you could have different derivatives. So you can imagine that if you were to draw a tangent line right there, you could draw multiple ones off of just that one. And so that's kind of where it comes from. But more importantly, this reveals that second derivative reveals what type of concavity that a function will have present. And you might be like, what does this even mean? And so that's what we're gonna figure out right now. Okay, so basically, what to be able to like apply, differential calculus, we kind of have to keep these rules kind of like as the backbone of like what we do. And so just by keeping these rules in mind, we'll be able to like solve a lot of problems. So the first rule is if the gradient of the second derivative, so like the rate of change of the rate of change, if that's increasing or positive, it's concave up. And so we see this function notation right here basically saying that if the second derivative is positive, so greater than 0, then it's concave up. And then if the gradient is decreasing of that second derivative, then it's concave down. And so we see that if that second derivative is less than 0, so negative, then it's going to be concave down. And so like this is explained by like graphical behavior. And so like right here we see how we have like different rates of changes right here, different derivatives. And so like this is like the original functions but based on the second derivative. And so we see how like the derivatives are going to be positive, but as you start going up they get less positive until ultimately they're negative, or like decreasing. And so as we see that occurring, it's concave down. But then you have this graph right here where it starts as negative, and then it's getting less negative, and then it becomes positive, and so it's concave up. And so that's kind of where those rules come from. And just by keeping in mind that idea, that will help you like sort of memorize it, or just like keep that in the back of your mind. But anyways, like, what does that even mean? Like, how are we able to apply that? And that's what we're gonna get into. So one of the primary things that we can apply that information about concavity is to stationary points, which are the points at which the graph is not increasing or decreasing, and these are otherwise known as the maximum and minimum. So the local maximum and local minimum. And so usually we're able to find these out by setting the derivative of a function equal to 0 to figure out these points. And like, this may have us wondering, like, or like thinking back to, like, if only there was a way to know if it's a maximum or if it's a minimum. And that's kind of like where we say, oh, concavity perhaps will tell us, because we know that we know certain graphical behaviors tells us if it's a maximum or a minimum based on if it's concave up or concave down. Another thing that concavity helps us with, or just actually that second derivative helps us with, is with point of inflection. And this is where the concavity changes, and the derivative is 0. And so basically a good way to think about this is kind of like where the signs of the second derivative change. So when it goes from negative to positive, or positive to negative. And so like here we see this happening. So like here's like graphically what happens. It's kind of like this point where you go from it being concave up to it switching into concave down, and we can like figure out what that point is. Okay, so now that we know a thing or two about how concavity, second derivatives, and all of that works, we can actually apply it to an example. So this example asks, find the coordinates and nature of the stationary points of g of x equals 3x raised to the fourth power plus 2x cubed minus 4x squared. And so the first step is finding the derivative of g of x, and we know this because it's asking to find the nature of the stationary point. So that's referring to we have to classify it as in the concavity, as well as from what we found out previously, we know that in order to find the stationary points, we can set the derivative equal to 0. And so to find the derivative, we use the power rule, which you can actually refer to your booklet to figure that out, like the rules and whatnot. But basically, like, you just take the exponent and bring it over to the coefficient, and then just subtract 1 from that exponent. So what I got was 12x cubed plus 6x squared minus 8x, and so that's a derivative, and we're going to set that equal to 0. And so once we set that to equal to 0, we're going to have to do a lot of algebraic work, but we ultimately get that x is going to be equal to 0, and then x is going to be equal to negative 3 plus the square root of 105 over 12, and negative 3 minus the square root of 105 over 12. And that's just based on the fact that this was a quadratic, but we had to use the quadratic formula in order to figure out the roots, or like the x's, I mean. Anyways, step 2, now that we know like the different solutions, is to substitute those solutions that we just found back into the original function of g of x. And so we do that down here, and you can actually do that in your calculator, especially if it's a paper 2, by like typing the original function and then using second trace and value, and then just typing in these different values, so 0, and then what these come out to, which is 0.604 and then negative 1.10. That's what you approximately get. And so once you once you substitute those back into the original function, you get the coordinate 0.604, and then negative 0.619, and then you get the other coordinate negative 1.10, and then negative 3.11. And so those are your three stationary points. But it'll ask us to classify them as well, and so we're gonna do that too. So in order to classify, especially when you're just starting, sometimes it's best to just kind of have a chart just to be able to like reference to. Um, but basically, we're finding the concavity and deciding whether it's a local minimum or a local maximum. And so the first step is you actually have to find the second derivative, and with that you can just use a power rule, and you already have the first derivative that I wrote up here, and so all you're doing is just applying the power rule to get 36 x squared plus 12x minus 8. And then once you do that, you can actually plug in those solutions you just found, so like the x's you just found, into this function, the second derivative function. And what that will get you is, we have those original x's up here, and these are the values, or like the outputs of this, so like what they were equal to once you inputted those x's for them. And so for when 0 was inputted, I got negative 8. When 0.604 was inputted, it was 12.38 approximately. And when negative 1.10 was inputted, 22.36 was outputted approximately. And so what this tells us is, kind of going back to what we previously learned, this is a negative. So since this is a negative, it is concave down, and this makes sense because if take for example, if we had a graph that was increasing at first, if it was increasing at first, but then it started decreasing less, and then it started decreasing completely, so becoming a negative, well then that's concave down. So that's how we know that. And then for these two, these are positive, and so these were decreasing at first, but then they started increasing, and so that would make them concave up. And so because this first one was concave down, this 0, 0 coordinate is known to be a maximum, and because this 12.38 was a concave up, this coordinate of 0.604 dash negative 0.619 is a maximum. And then since this was up, then this coordinate right here is going to be another minimum. I meant to say minimum for this one as well. These two are minimums. And yeah, that's basically how we were able to find not only just the coordinates of the stationary points, but also classify them as we did right there. Again, the second example we're going to do is going to be referring to finding the coordinates of other points of inflection. So finding the points of inflection basically. And it's of this function f of x equals 8x raised to the fourth power plus 3x cubed minus 6x squared. And so step one to figuring this out is that you have to identify that the inflection refers to when the second derivative is equal to 0. And so to start off, we have to find the second derivative. So first you would find the first derivative by using power rule, as we do here, and then you find the second derivative by utilizing power rule again, and you can refer to your yellow booklet to figure that out. And so once you do that, you just set the second derivative equal to 0, as we did down here. It's going to be a quadratic, but the quadratic isn't going to be able to be factorable, so you have to use the quadratic formula. And once you use the quadratic formula, you get that it could either be negative 3 plus the square root of 137 over 32, or negative 3 minus the square root of 137 over 32. And so step 2 is that you substitute those solutions, so those x's that we just found, into the original function, so that f of x equals 8x raised to the fourth power plus 3x cubed minus 6x squared. And so once you do that, you get that the coordinates are 0.272, negative 0.340, and negative 0.460, negative 1.20. And those are your two coordinates, and that's basically how you find the points of inflection.